I'm Jonathan DeVerso, and I support the Second Amendment.
I'm Billy Ward, and I do too. For our end of the year physics project, we've been assigned to choose a physics equation and prove it experimentally. So the equation that we chose is projectile motion. And what that is, you guys are probably familiar with projectile motion, whether it's in the form of sports or shooting or anything. It's where you have an object and you launch it, whether in a straight line, in some sort of an arc, or vertically. And what our goal is to calculate how far it'll go. So one of the best examples of projectile motion I can think of is what I see every year at the World Championships of Pumpkin Chunkin', which I attend every year. And this is our pumpkin chunkin' machine, but unfortunately, we just don't have the room around here to see how far it'll go, because this thing will shoot over half a mile. So that's not going to work in my backyard here.
I'm Adam Savage.
And I'm Jamie Heineman. We're in the pits with 110 competitors that showcase everything from human-powered catapults to gigantic air cannons.
Pretty simple. The team that launches an 8 to 10 pound pumpkin the farthest wins the championship.
I am really feeling good this year. I feel like we're the team to beat.
You know it's a good throw. When the frickin' thing goes out of sight, it was a screamer.
We're about to drop some bombs right now, so I'm about done with you guys because I got to get to work.
Being one of the crowd favorites at the Chunk is no accident. We put on a great show.
Now for the fun part. If you're out there throwing pumpkins in the field, you're having fun.
So what we have here is this is a miniature version, and they both work in essentially the same way. This one's a little bit more complicated, but it's the same idea. You have an air tank in the back, you pressurize that, and then when you open the valve up, the air comes out. It wants to escape because it's under pressure, and that'll push out your projectile, whatever it is, whether it's a potato, a pumpkin, a bowling ball, anything of that sort.
So the equation we're trying to prove is one of projectile motion. The equation we're going to use is distance times half the original velocity plus the final velocity multiplied by time. In other words, the distance will be found by finding the average velocity multiplied by the time. So in the end, the final velocity will be 0, but we have to find out what the original velocity will be. So in order to do that, we will be using a high-speed camera to find how much or how fast the potato will go once it first leaves the barrel of the cannon. And after that, we can use another equation to find the time that it will fly in the air, but we need to find the original velocity before we do that. So it took 11 frames in the 60 frames per second the camera films at, and 11 divided by 60 will give us the time. So in 20 feet, it went over 11 over 60, which would be the time, and we got that to equal 109.09 feet per second. Converted to meters would be 33¼ meters per second. But this would only be in one direction, so we're going to have to find the different components of how fast it is going. So while the total speed would be 33.25 meters per second, in the x and y directions it would be moving 23.51 meters per second instead. So we use the equation final velocity equals the original velocity plus acceleration multiplied by time. The final velocity would be 0 because we are trying to solve for the max height, and at the max height it does not have a velocity. And the original velocity we found out to be 23.51, and added to that is the negative 9.8, which would be the force of acceleration due to gravity multiplied by the time. So we moved the 23.51 over to the other side, so to the negative 23.51 would be equal to the negative 9.80 multiplied by the time. When we solve for the time, we get the time equals to 2.40 seconds, and to account for the time it has to come down as well, the total time in the air would be 4.80 seconds. So using this, we can now plug this into our original equation, which is the distance is equal to half the original velocity added to the final velocity multiplied by the time. So with solving for this equation, the distance would be 56.42 meters, or 185.1 feet.
So we're ready to fire here, and two things I wanted to make note of is, first of all, I got my my gauge here, or digital level, to make sure we're at 45 degrees, and we're pretty close there, 46, 45. We're about as close as we're going to get it. Our pressure, we always got to keep our pressure at the same point, because otherwise that's going to change the velocity. So I'm firing right about 20 psi. By the time we fire, it'll probably be down to 20. It's got a slight leak. And we have signs going down the yard. Each one is 30 feet from the other. So that way, wherever it lands, it's measured from that point down to the distance. So here it goes. Ready?
Ready?
Alright, let's go check it out. Just over 191 feet. This sign right here is 180, so that's 11 feet there. Pretty close, I'd say.
Alright, right now we're going to do a second test launch of the potato cannon to confirm our results.
Ready?
Ready. So the potato we launched went about 198 feet from where it was launched from. This was slightly larger than our prediction, but due to the tailwind that was experienced during the flight, we're going to go back and check our math and find out how much that had to play in this launching of the potato. So the first time we tested our potato cannon, the first potato went 12.9 feet longer than our prediction. The second time we performed the test, it went 5.9 feet longer than we predicted. So why do you think it went that far?
Well, you know what that could be is we had a pretty decent tailwind actually, so that'll give you a lot of distance. Like when we're down in Delaware, actually one of the things we'll do is with the air cannon, if we got a tailwind, we'll make our angle higher, and it'll get up there, and the the wind will carry it farther and stuff. So it could have something to do with that. And you know what else? It could be a slight difference in the weight of potatoes.
Probably.
Not a big difference, but enough that one was slightly lighter, slightly heavier. That's why we were had a small difference. But 5.9 feet, that's pretty close.
It's pretty accurate.
Yep. All right, let's go shoot something.
Let's do it.
That's how we do our physics projects.